Good evening, everyone. I'm Professor Andrei Zvelindovsky, Head of School of Mathematics and Physics at University of Lincoln in the United Kingdom. Very well welcome to everyone who came to our Astro-Chat. And as already became tradition, we joined via internet link by Professor Don Kurtz. Hello, Don.
Hello, Andrei.
There is some distance between us. Don physically in South Africa. And thanks to this wonders of computers, we can chat about various astronomical things. Some of you are already our regular visitors, but some maybe just came for the first time. So I usually say just a few words about Don. Don is well known in the world, in particular in the field of astroseismology. He originally is from California, San Diego, where he started and finished his undergraduate study, followed by research doctorate, PhD in University of Texas in Austin, which followed by a quarter of a century work in University of Cape Town in South Africa. After that, in 2001, he moved to United Kingdom and spent over 20 years working in University of Central Lancashire, from which he retired in 2020 and became Professor Emeritus. In the same time, Don also became extraordinary professor in Northwest University in South Africa, where he is physically now. As well, he is a visiting professor of astrophysics at the University of Lincoln here with us. In his longest distinguished career, Don published over 500 of scientific papers, as well as already classical textbook in astroseismology. He served as vice president of the Royal Society or Royal Astronomical Society, spent thousands of hours observation time in telescopes, and most recently, just about 2 months ago, if I'm right, Don was awarded Royal Astronomical Society 2022 Service Award, in particular to his promotion of astronomy to a wider audience. We're very happy to have Don with us again tonight, and the topic of his chat today will be about time. Floor to you, Don.
Thank you for the introduction, Andrei, and good evening, everyone. It's nice to be back for our next Astro Chat. If you'll bear with me for just a moment now, I'm going to share my screen with you. And I hope that that has done it. Andrei, can you tell me, am I live?
Yes, we see now your screen. It's about time.
It's about time. What is time? You don't think about that so much anymore. You probably did when you were younger. But if you really puzzle over that question, you'll find that it's very difficult to come to an answer. Do you think of time as Isaac Newton did, as a river flowing along with the past over here and the present here and the future off in that direction? Science fiction loves the idea of time travel. And of course, if you think, well, if we could only find the technology, time travel might be possible. If you're thinking like that, then somehow you think the past exists somewhere out there and the future exists. It's entirely possible that that's not true and that there is only the infinitesimally thin present and that the past and the future don't have an independent existence. I don't know the answer to that. That's a really hard question. And so to prepare this talk, I went to the dictionary and looked up to see what it had to say about what time is. And it said time is a measured or measurable duration. And I didn't feel very enlightened by that. So I looked up what a duration is and found the dictionary thinks that that's a time. That doesn't get us very far. Time's a duration is a time. And I'm going to leave you to puzzle for yourself over that question, what really is time? And instead, tonight, we'll talk about the measure of time. The day, the month, and the year all have got astronomical origins. And you probably think you know what the day, the month, and the year are. And maybe you do. Maybe they're not quite what you think. And we'll look at that in the coming 20 to 30 minutes or so. The week's got a semi-astronomical origin, and I'm going to tell you the story of how the days of the week got their names. Hours and minutes and seconds are entirely invented by humans. The day itself, well, here's a beautiful picture of the plafond at the Salle de Conseil du Observatoire de Paris, the boardroom ceiling in the Paris Observatory. It's a painting of Venus passing in front of the sun. Let me pull up my laser pointer here. As the sun's being pulled across the sky by the charioteer in classical mythology, and there's an astronomer down here watching Venus transit the sun. This was in honor of the 1882 transit of Venus. And so the day is the time it takes the Earth to rotate on its axis once, right? Not quite. And so let's look at the reality of that. Here's a little diagram that I drew on the computer. It's definitely not to scale, but there's the sun at the center of the solar system, and orbiting about the sun, here's the Earth's orbit. And this bottom image of the Earth that I drew, that arrow points towards the sun to indicate that at that point on the Earth, it's noon on that day. When the Earth rotates once on its axis 360 degrees, it also orbits 1 degree around the sun. And so when it's rotated once on its axis, that arrow is not pointing back to the sun. It's not quite yet noon again. The Earth has to rotate another degree to get back to noon. And so the 24 hours that we keep on our clocks is the time it takes the Earth to go from noon to noon, not the time it takes to rotate on its axis once. That time, called the sidereal day, is 23 hours, 56 minutes, 4.1 seconds. And you can see by the time the Earth is rotated a quarter of the way around the sun, 3 months later, an exact number of rotations would have us pointing in that direction. The Earth actually has to rotate an additional 90 degrees by then to get back to noon. The Earth's rotation is not constant. The Earth is not a good clock. Now, we in physics have got a concept called the conservation of angular momentum. Angular momentum is spin. It's a measurement of how fast an object is spinning. It depends on the mass. It depends on the rate of spin, the velocity, and it depends on how far that mass is from the rotation axis. So the thing that is conserved is the mass times the velocity times the distance from the rotation axis. And here is a championship skater, and she is about to demonstrate a world record spin. And you'll see that when she starts to spin, she has her arms and leg out. And then as she pulls them in, the mass is coming closer to the rotation axis and she spins faster and faster and faster. Well, the Earth is also rotating and it's conserving angular momentum. The length of the day is not constant because the shape of the Earth changes with the tides in the Earth. When the moon and the sun are in the same direction or in opposite directions at either new moon or full moon, the tidal bulge is bigger. And so that's like the ice skater putting her arms out and the Earth slows down. And then at third quarter or first quarter moon, when the bulges from the sun and the moon pull in different directions, the bulge is not quite so big. That's like her pulling her arms in and the Earth speeds up. And that changes the length of the day by about 1/1000th of a second. The Earth's rotation also varies with changes in the wind speed, changes in ocean currents, with seasonal variations and longer-term variations. And that can change the length of the day by several thousandths of a second. And you're thinking to yourself now, well, who cares? I'm never going to notice a change in the length of the day by 1,000th of a second. But we physicists like Andrei, astronomers like me, we care about that 1,000th of a second. It matters to you for your GPS, positioning you when you're using your phone and using your GPS to find your way around. But in astronomy, just as an example, those pulsars, that I talked about previously can spin up to 1,000 times per second. And if your day changes by 1,000th of a second, you can miss a whole rotation in observing a pulsar if you don't keep your time accurately. So we keep time by atomic clocks. And atomic clocks are precise to nearly a millionth of a millionth of a millionth of a second now. We can really measure time to high precision. So every 2 years or so, we get something called the quasi-biennial southern oscillation. When the Southern Ocean, Pacific Ocean heats and currents flow to the east up against South America, that typically happens around Christmas time in December. And as a consequence, when that warm water comes up against the coast every couple of years, and it's around Christmas, the Chileans call that El Nino. Well, Nino in Spanish means the boy child, but with a capital N, it means the Christ child, and this just associates it with Christmas. When that ocean current flows to the east, it's carrying spin with it, but the Earth has to conserve angular momentum. So when the ocean spins to the east more, the entire Earth slows down. And we astronomers can measure the spin of the Earth so precisely that we see the day getting longer before the weather starts to change with the El Nino. We can see that coming before the meteorologist can pick it up. And that is, of course, very important for our global weather. It changes rainfall patterns, drought patterns, and we can follow it with astronomy. Now, this is a real picture of the Earth and Moon taken by a satellite that was out beyond the Moon, looking back to the pair of them. And you'll notice how much smaller the Moon is than the Earth. You notice how dark the Moon is. It's covered with basaltic lava so that its true color is nearly black, in contrast with our beautiful bright Earth with its white clouds, blue ocean, and even more reflective ground than the dark black basalt on the Moon. Well, the Moon and the Earth interact via tides. The Moon causes both land tides and tides in the ocean, and it's tugging on those tides, and that's causing the Earth's rotation to slow down. The day is getting longer. That means the Earth is losing angular momentum because it's spinning more slowly with time. And that angular momentum is being transferred to the Moon. It's not making the Moon spin faster. It's the angular momentum of the Moon orbiting the Earth, and that's getting larger by the Moon drifting away from the Earth. It drifts away by about 4 centimeters per year, and we can measure that directly. We bounce laser beams off of mirrors that were left on the surface of the Moon by the astronauts decades ago, and we can measure the distance to the Moon to a precision better than 2 centimeters and watch it drift away. As time goes by, eventually the day will be longer than 40 hours. And as the Earth slows down to keep its rotation time in sync with our atomic time, we add leap seconds as we need to, usually on December 31st at midnight. Stop the clocks for a second, add a second, start them back up again to keep the atomic time in step with solar time or Earth rotation time. When we add time into the calendar, that's called intercalation. Now here's a chart, which I've taken from NASA. There's the website down there, showing the number of days in a year and the number of hours in a day as we go back into geologic time. There in the late time of the dinosaurs, at the end of the Cretaceous, when the great asteroid struck and the dinosaurs went extinct, the day was slightly shorter than now. If you go back, for example, to the Cambrian, when life came out of the sea to first come onto the land, the day was only slightly less than 21 hours long. What would happen to you and to me if all of a sudden the day were now 21 hours? And the answer is we wouldn't survive. We could not handle that. Because if you're going to live by the sun, that would mean every day you would have to get up 3 hours earlier. Let me guess that you got up at maybe 6 or 7 o'clock this morning. Well, if you got up at 6 o'clock this morning, if we went on a 21-hour day, tomorrow you'd have to get up at 3, the next day at midnight, the next day at 9 p.m., and so on. We physiologically wouldn't handle that. Of course, animals and plants adapt slowly via evolution to the slow changes in the length of the day, but just realize that the Earth is not a good clock, and using it to keep time over long periods doesn't work at all because of the change in the rate of the spin. Now we divide we divide the day into 24 hours, and that goes back to the Babylonians. Babylonian culture really dates from about 4,000 years ago up to about 3,500 years ago was the heyday of Babylonian culture. It is, of course, the illustrious history of modern-day Iraq, not doing as well now as it was at the time of the Babylonians. We hope it will recover. The Babylonians like to count in groups of 12 rather than groups of 10, and that makes a lot of sense. We still like groups of 12 too. If you go out and buy eggs, you buy them by the dozen. You buy donuts, you buy them by the dozen. And the reason is you can divide 12 up into 2 6s or 3 4s or 4 3s or 6 2s. It's got many divisors. 10's not quite so good for that. So when we're dividing things up, we like to divide in 12s. They use 12 as their basic counting system. And so they had 12 hours during the day and 12 hours during the night, but they always had 12 hours during the day. And so in the summer, the hours were long, and in the winter, the hours were short, vice versa for the nighttime. That fixed length hour didn't arise until decent mechanical clocks were invented, and that was in the 1400s. One of the most beautiful of the early mechanical clocks like that still exists is the clock on the town hall in Prague. And many of you will have been to Prague and seen that beautiful astronomical clock that's there that did keep constant hours once we could keep time that precisely. Now, the Babylonians also had 7 days in their week. Now, you might think that we've got 7 days in the week because there's 7 days in Genesis in the Old Testament of the Bible. But that's almost certainly there's 7 days in the Bible because the people who wrote the Bible already were living on a 7-day week coming out of previous cultures. And we ask why 7 days in the week? And the answer is because of the number of planets. And this word planet comes from a Greek word meaning wanderer. The planets are the 7 things in the sky that move through the stars. Those are Mercury and Venus, and not the Earth. It's not in the sky. We're standing on it. So Mercury and Venus, Mars, Jupiter, and Saturn, the sun and the moon. And the Babylonians, of course, didn't know what those things were. They were just lights in the sky. But mysteriously, those 7 moved through the fixed stars. And the Babylonians came up with an idea as to why that should be. The planets move through the stars because the planets are gods. And the gods do as they please. And that, of course, is the source of the religion astrology, where astrology believes the planets are gods and the gods can affect people. Of course, we know the planets are not gods now. We've been to them, and there is no scientific substance of any sort to astrology. The planets to the Babylonians were ordered from the most powerful god, Saturn, to the least powerful, the moon. And the reason for the order of the power, well, Saturn takes 30 years to move around the sky. It moves the most slowly. And as you know, in human society, the most powerful person sits behind a desk and doesn't move at all, ordering other people to run about and do the job. So Saturn was the most powerful god. Jupiter, the next most powerful, taking 12 years to move through the sky. Then Mars, the sun in reflex motion from the Earth, Venus, Mercury, and the moon. Of course, in Greek mythology, you might be thinking to yourself, well, is Saturn really the king of the gods? I thought it was Jupiter. Isn't Jove the king of the gods? Well, Jove was to the Romans. There was a prophecy given to Saturn that he would be usurped by his children, one of his children. And his solution to that was with each child that was born to him by his wife Ops, he ate the child. And when it came time when Jupiter was born, Ops did one of 2 things. There's different myths. Either she secreted Jupiter away and fed Saturn something else that fooled him into thinking he was eating the child, or she gave Saturn something to make him sick and he brought Jupiter back up. But in any case, Jupiter was very angry about this when he grew up, and he did usurp Saturn and become king of the gods. Now, in the Babylonian religion, every hour of every day was given over to one of the gods. And so the first hour of the first day belonged to the most powerful god, Saturn, and that was Saturn's day. The next hour to Jupiter, then Mars, Sun, Venus, Mercury, and the moon, and then down through the list again and again until after 24 hours, the first hour of the next day belonged to the sun. So following Saturn's day was Sun's day. And then down through the hours again until following Sun's day was Moon's day. And I think even though this is 3,500 years old, you're probably finding it familiar. Saturn's day, Sun's day, Moon's day. But notice it jumps 3 each time. Let's continue with that. Following Moon's day is Mars's day, Mercury's day, Jupiter's day, and Venus's day. And now it doesn't sound quite so familiar in English. But if you go to the Romance languages, the weekend days have been changed for religious reasons, but look at the names of the days of the week in French: lundi, mardi, mercredi, jeudi, vendredi, or in Spanish, lunes, martes, miércoles, jueves, viernes. You can see the planets there: the Moon, Mars, Mercury, Jupiter, and Venus. What happened in England? What happened in Lincoln is that the Vikings came. Vikings came to Lincoln in the 9th century. They brought with them their gods, and they, of course, integrated with the native people of the British Isles. They stayed, and Mars, Mercury, and Jupiter and Venus got replaced in English by 2, Woden, Thor, and Freya, the Norse gods, leaving us with Saturn's Day, Sun's Day, Moon's Day, Tuesday, Woden's Day, Thor's Day, and Freya's Day. This tradition is 3,500 years old. We humans are really very, very traditional. The week itself, the 7-day week, hasn't been broken for about 1,800 years. 1,800 years ago, today was a Friday. Nothing else in the calendar is that stable. The year, you think the year is the time it takes the Earth to orbit the sun, but that's not true. The time it takes the Earth to orbit the sun is 365.2564 days, a little bit longer than 365 and a quarter, but the Earth spins like a top, and its axis is tipped to its orbit about the sun, and the gravity of the sun and the moon tugging on the Earth cause it to precess. It wobbles with a period of 25,800 years. The year that we use is the tropical year. It's the time from the start of the vernal equinox in spring in the northern hemisphere to the next vernal equinox. And because of this precession, that is 365.2422 days, just less than 365 and a quarter. That's what Western society has been trying to build calendars on for over 2,000 years to match that number. It began with the Roman Republican calendar prior to the Roman Empire. The Republican calendar had only 10 months in it. In winter, they didn't have any months. And the year started in March. Martius, and then Aprilis, Maius, Junius, and then just 5th, 6th, 7th, 8th, 9th, and 10th months. Some smart spark realized the moon kept going around and decided to name the months in winter, and they were named Januarius and Februarius, and they got tacked on to the end of the year. Notice March was the beginning of the year. But the year was lunar. The time it takes the moon to go through its phases is 29.53 days. It's not the time it takes to orbit the Earth, that's shorter, but the time to go through its phases, 29.53 days. And so the Roman Republican year was short by 10.5 days, and approximately every 3 years, another month would be thrown into the calendar. And that month was thrown in after February the 23rd. There's no historical understanding of why that date was chosen. And then after the new month every 3 years, the last 5 days of February followed. This is the reason why our leap year, when we add a day to the calendar, it's in February, but we at least slipped it to the end of February instead of keeping it after February the 23rd. In Roman England, and in England's colonies, March the 25th was the start of the year until the year 1752. And so if I may, right now, today, wish you Happy New Year on the Julian calendar. If we were still on the Julian calendar, today would be New Year, March the 25th. I hope you celebrated New Year's Eve last night. The vernal equinox is the start of spring in the Northern Hemisphere, and that was just a few days ago. In fact, it was on Monday. It was on the 20th of March this year at 5:30 in the evening there in Lincoln, if that's where most of you are. By the year 46 BC, the Roman Republican calendar had slipped because of the extra 10.5 days. It was differing by the astronomical equinox by 3 months, and something needed to be done. And so Julius Caesar commissioned an Alexandrian astronomer, Alexandria being in the north of Egypt. His name was Sisigines, to revise the calendar. Now, all over the Roman Empire, you can find memorials to Julius Caesar. There's a typical bust of him. I don't know of any bust of Sisigines, but we astronomers have given him a very nice crater on the moon. So there's crater Sisigines on the moon. It's about 17 kilometers, a little over 10 miles in diameter. And Sisigines decided something you're familiar with. The year's got 365 days, but every fourth year we add an extra day. And in his time, it was added after February 23rd. It sensibly slipped to the end of February. I think it would be even more sensible if it slipped to be right after December 31st and we just had a second New Year on leap years. Perhaps that's something we'll do some year. Sisigines decided that January 1st would be the start of the year, but the people didn't accept that. And governments can pass any law they like. If the population won't obey the law, it is no law. And that attempt to get January 1st to be the beginning of the year didn't work. And so it wasn't until 1752 that that finally happened in England. The length of the month was either 30 or 31 days, except poor old February. So the month was taken away from the time it takes the moon to go through its phases. To fix the calendar, the year 46 BC had an extra 3 months in it to get the equinox back to that magic March the 25th. And that was known as the year of confusion. And you can expect, how would you be confused if, for example, instead of having April next month, in another week and some days, we instead had 3 more months and then we went back to April? That might produce substantial confusion in everybody's schedule. But the calendar, although it looks like it's under control, is not, because the Sisigines' calendar, the Julian calendar, is 365 and a quarter days, and the real calendar is 11 minutes and 14 seconds shorter than that. And so by the year 325, more than 3 centuries later, the vernal equinox had slipped back to the 21st of March, where it typically is today. That's how it got to the 21st of March. Why did it get left there? Because there was a council in Nicaea in Turkey. Nicaea is modern-day Iznik, and I've put over here on the right a panel of a beautiful Iznik tile. That's what Iznik is famous for now, is its glorious tiles that they make. The Council of Nicaea was to set the religious holidays. The calendar wasn't being reformed for farmers. Farmers know when to plant. They can judge the weather. The calendar was being reformed for the priest's need in the church, this being the Catholic Church, the only Christian church then. The priests need to set the religious holidays, particularly Easter, the second most important holiday in the Christian calendar. And so the Council of Nicaea set the date of Easter to be, and in case you never knew, this is the rule for Easter. It's on the first Sunday, following the 14th day of the moon. Now that's not quite full moon. Full moon's about 14.76 days into the moon cycle. But this is the ecclesiastical full moon, following the 21st of March, which is defined by the church to be the vernal equinox. And so, for example, this year, when the astronomical vernal equinox happened on the 20th of March, last Monday, the ecclesiastical or church equinox was on the 21st of March. It always is. And there's the rule that defines Easter, but because it depends on the phases of the moon, it can slip around by more than a month, I think, as all of you know. It's the reason you usually have to look up when Easter will be on a calendar, rather than just knowing when it comes each year. But they didn't fix the length of the year at the Council of Nicaea. By 1582, the vernal equinox had slipped back to the 11th of March, and now there's a problem with setting the date of Easter. So in 1472, Pope Sixtus IV invited a German astronomer named Johann Müller, we know him by a Latin name, Regiomontanus, to Rome to reform the calendar. Müller was assassinated. Why would somebody assassinate some poor astronomer up here who's just trying to fix the calendar up? And the answer is because if you're going to pray to your patron saint on your saint's day and somebody changes the calendar, what if your saint's not listening? The saint's going to know about this change? If you mess about with people's religion, and that's what messing about with this calendar did, you can get into trouble with fanatics. And you know that's true today. You can get into trouble with fanatics. They take their traditions very seriously. Sixtus, you might know in his adjectival form, the adjective of this particular Pope Sixtus is Sistine, and he is the one who commissioned the Sistine Chapel, which was, after he died, decorated by Michelangelo. Because Regiomontanus was assassinated, the reform of the calendar didn't finally happen until 1582. Pope Gregory XIII then got two astronomers, first Luigi Giraldi, who died naturally in 1576, and then Christopher Clavius completed the work. And they fixed up the Julian year, which is too long by 1 day and 128 years, and they did that by taking out one leap day out of the calendar every keeping century years, they take 3 days out of the calendar every 400 years, which is close to 1 in 128 years. So in the Gregorian calendar, century years are common years. They're not leap years, unless they're divisible by 400. So the year 2000 was a leap year. 2100, 22, 2300 won't be, but 2400 will be again. And that gets the calendar down pretty close to the tropical year, but it's not quite right. And there have been suggestions that we astronomers, the International Astronomical Union, who you as citizens of the world give us the right to control the calendar and decide on these reforms in consultation with all the world's governments. It's been suggested that we should make a rule that we take out one more day every 4,000 years to make the calendar more precise. And our commission that works on that with the International Astronomical Union has two basic answers to that. One is, what's the hurry? And the second one is, well, you know, the Earth's rotation is just not constant. It speeds up and it slows down in unpredictable ways. And it's best to leave that for 4,000 years from now when it's clearer what the Earth's rotation's doing in terms of reforming the calendar. So in 1582, Pope Gregory declared that the Feast of St. Francis, the 5th of October, would be followed by the 15th of October in order to get the vernal equinox back to March the 21st. Of course, the Catholic countries did what the Pope said, but 1582 is post-Martin Luther. 1582 is post-Henry VIII. And the Protestant Eastern Orthodox countries didn't follow that rule until later. In the case of the Protestant countries, well, England and the colonies made the change in 1752, by which time the calendar was off by 11 days. Parliament decreed that the 2nd of September of 1752 was to be followed by the 14th of September. They pulled 11 days out of the calendar, and they pushed the first of the year to January the 1st, and this time it took. So 1752 in England started on March the 25th. 1753 started on January the 1st. Obviously, September 1752 was a very short month, and there is a myth, an urban myth, that there were time riots, where people were saying, give us back the 11 days you've stolen from our lives. They thought their lives had been shortened by 11 days. Workers wanted a full month's pay. Landlords wanted a full month's rent. That is all urban myth. None of that happened. It arose from a painting by William Hogarth. This painting is in one of the greatest little eclectic museums in London, Sir John Soane's Museum. It's on Lincoln's Inn Fields. Sir John Soanes was the great architect. He designed the Bank of England, many other monumental buildings in the city of London. And his home itself is a beautiful home, and he collected many things. And among them are these gigantic paintings of William Hogarth. To see them all, you've got to go in when the curator is actually opening the paintings and pulling them back on their hinges. And one of them is this painting here of the people partying because of the 11 days they've lost from their lives. They're drunk, they're happy. This man back here looks like he's about to smash the window with this stool. This man here is pouring a jug of wine over this drunk who's sitting on the floor. And the drunk on the floor has his foot on a poster. And that poster is not readable in this reproduction, but in the original painting, if you look at it, it says, give us our 11 days. And that's the source of the myth of the English time riots. That still impacted on UK society. The first of the year was tax day. So March the 25th, 1752, the bankers paid their taxes. March the 25th, 1753, the government said to the bankers, pay your taxes, and the bankers said, it's not been a year since we paid you last. You waited another 11 days. You took 11 days out of the calendar. And in an argument between the government of the UK and the bankers in the city of London, as usual, the bankers won. And so count the 11 days, that pushed the start of the tax year to April 6th, in case you've ever wondered why it's got that weird starting date. Well, the Orthodox countries never did change. The calendar is now different by 13 days. Here's an email I sent to Andrei last January. You can see I sent it to him January the 22nd. He was at home at that time with his family in Odessa, in Ukraine. And there I just said, Happy Christmas today, Andrei, for the 7th of January. Why does the Ukrainian Orthodox Church celebrate Christmas on the 7th of January? And the reason is they're still on the Julian calendar for the Orthodox Church. And now there are 13 days difference. And there I've put them on this calendar. You can count them. There's Christmas Day on the Gregorian calendar. But if you pull 13 days out of the calendar, then following Christmas Eve is, there it is right there, 7th of January on the Julian calendar, Ukrainian Orthodox Christmas. Well, I think all of you have read Alice's Adventures in Wonderland. And you may remember that the Hatter sang it to the court, and the Queen of Hearts was so offended at the Hatter's terrible voice that she accused him of having murdered time. And old man Time himself took offense at that and stopped time for the Hatter. It was perpetually forever for the Hatter, tea time, 6 p.m. So time stopped for the Hatter. It hasn't stopped for me. And so it's time, folks, that I stop talking and we begin to take your questions. Thanks for your attention. Back to you, Andrei.
Thank you very much, Don, for this wonderful presentation.
Unmute yourself, please, Andrei.
Oh, I think you can hear me now. Yes, we are online.
Yeah. I'm not hearing you, Andrei. Is that my problem or yours?
I think something with your speaker, because I can hear me. And people in the live chat, if you push plus, that you can hear.
I'm going to have trouble taking questions from you lip reading, Andrei. Sorry, I really can't hear you. Oh, this is an interesting problem. I cannot hear you. Okay, Andrei, can you hear me? Nod your head yes. Can you hear me? You can hear me. Okay, I can't hear you. Am I still sharing?
Can you hear maybe now?
This is an interesting problem. Sorry, folks, I can't take your questions and answer them unless I can either read them for myself or Andrei can pass them on to me. Sergey, can you help what's happening here? This is not a problem we've had before. Yes. Andrei, a choice could be as if I log out completely and you re-invite me to the meeting.
Yeah, it's okay. Yes. Yeah.
Okay.
Yeah.
I'm on my way out.
So we'll see Don in a second, hopefully. And in meanwhile, yes, very happy that people came from all over the world. We have people from Texas and from New York, and also from here, from Lincoln and nearby, Skegness, and it's really pleasure to see. So we just need to wait and Dawn really reappears. Yes. Apologies for this. Yes, thank you. We just need to connect within this international space. Right, okay. Just let's see, Dom should appear again. Thank you for the audience. Yes. Can you hear Don now?
My speakers are muted. Unmute. There we go. Let me see if I can hear you.
Me?
Yes, great. Sorry, folks. I'm back. Phew. Technology.
Thank you. Yeah, so we again connected, and as I see Minerva Bird said, we have time. So I just remind everyone, if you type your questions in the live chat, I can read them to Dawn, and we have about 20 minutes still, or a little bit more, because of this disconnection, that we can give Dawn a chance to answer. And it was actually a question when, or just a comment, then then presentation was running. That was from AC, who is our regular visitor, who said that 8.9 magnitude earthquake in Japan has shortened Earth Day by 1.8 microseconds, NASA says. So maybe, Don, you would like to comment on that.
Well, thank you for that comment, AC. AC's, for the rest of you, is commenting from San Diego, which is also very familiar with earthquakes. And so what must have happened with that AC is, with the thrust on that Pacific plate moving underneath the Asian plate in Japan, it would have slightly reduced the Earth's net radius for its mass about the rotation axis and changed the length of the day. And just for your information, I was 10 stories up in my office at the University of Tokyo when that earthquake hit. It got my attention.
Thank you. So could be that also reason then, when you show a table of length of day, long back in time, then was not really kind of monotonic function. It was like a bit shorter, a bit longer, like millions and millions years ago. Is it because of impacts and that sort of stuff?
No, Andrei, that table didn't have all the geological periods in there. I didn't make that table up, but there were geological periods missing and skipped. Those of you who know them will have noticed the Triassic was there, the Cretaceous and Triassic, but the Jurassic was missing. And so it's a more smooth function than that. And it's a simple interaction of Earth's spin going into moving the moon farther away, picking up the orbital angular momentum of the moon. And so when the day was shorter, the moon was closer. It was bigger in the sky. Dinosaurs got to see a bigger moon.
Thank you. There is a question about El Nino from Jane Elizabeth Madison. How will climate change, which impacts things like El Nino impact time?
I don't know the answer to that, Jane, and I'm not sure that anybody has got a model that can predict what that will do. That semi-biennial, quasi-biennial southern oscillation comes from a heating in the Pacific Ocean on a period of around 2 years. And with a complete change, even small change in the Earth's, not just climate, but its mean temperature, that possibly could change, but I don't think any model can provide an answer to that. So I'm saying to you, I don't know, but I don't think anybody knows that.
Thank you, Don. Now a question from Anthony Bloxham, who asks that, how were the seasons devised, and why do we have a 1 hour difference between summer and winter time?
Oh, well, the seasons are a human construct. Well, they're not a human construct. I mean, obviously there is summer and winter, spring and autumn, but dividing the seasons into 4, that's cultural. Japan has many, many more seasons. They have a rainy season and a humid season, and obviously spring flower season, and their seasons can be as little as 3 weeks long. So naming the seasons is cultural. But I mean, obviously there is spring when the growth comes, and there's summer, and then there's autumn when the things die back. Your answer about the 1 hour change in summer, that's entirely a civil decision to push the clocks forward. And you know, you don't need to do that. What you could do is just say, you know, it's summertime and the days are really long. Let's all get up 1 hour earlier and go to work an hour earlier and get home an hour earlier so we can enjoy a longer evening. And everybody will groan and say, oh, no, I can't get out of bed an hour earlier. I have trouble getting up at the normal time. And so you just change the clock and then they do exactly that.
Thank you. Thank you. There are quite a few questions. So there is a question here from Andy Ellison. Presumably when space probes do flybys of the Earth, that also affects the rotation period of Earth?
Oh, Andy, yes, and it affects the Earth's orbital period around the sun too. So we scientists, the engineers, the space agencies have been using the Earth and the other planets as a slingshot to get out to the outer solar system on the cheap. So we sent out, if we take a satellite, let me think, the Cassini mission, which went to Saturn. It's now dead. It was destroyed to keep it from crashing into any of the moons. But when it went out, it first went into Venus and then whipped around Venus. And in interacting with Venus and the sun, that gave it more energy to go farther out in the solar system. It came back past the Earth and grabbed a bit more energy. And so that satellite took energy from both Venus and the Earth to get to the outer solar system. So we didn't have to pay to burn fuels to get it out there. And that energy lost from the orbit of Venus and the Earth has moved them slightly closer to the sun. But the mass of the satellite is so tiny compared to the planets that that's not measurable for us. And so, yes, that interaction could be tidal to and change the rotation, but that's going to be so infinitesimal compared to these huge changes of milliseconds on a yearly scale. We would never pick it up. But in terms of the absolute physics, you're right, that would happen.
Thank you. Thank you, Don. Now, there is a question from a member public with a nickname Twitter689. It's about Albert Einstein theory of general relativity, or more specifically, if physicists did measure time dilation.
The answer to that, Zwitter, is yes, there are two kinds of time dilation. There's special relativity, which came in 1905 with Einstein's theory of special relativity. And that is that if you are traveling faster than I am, I will see your clock running more slowly. And that is a real effect. We measure it quite easily. Particle physics, we can take particles which have got short lifetimes, like muons, for example, a lifetime of a millionth of a second, and accelerate them up to nearly the speed of light, and their lifetimes grow longer and longer and longer from our point of view. That's one kind of time dilation. The other kind of time dilation is gravitational. That's general relativity, which came not 1905, came 1915, 1916, when Einstein published general relativity. And the deeper you go into the gravitational field, the more slowly your clocks will run. And so if you put a clock on a satellite orbiting the Earth, it will run more slowly because it's moving at 7 kilometers per second. It's moving at a high speed, but it will run more quickly because it's higher in the Earth's gravitational field. And I used to make my undergraduates, not first year, they weren't too good at what we call linearizing the equation, but the later students, I would have them calculate at what orbital height would a clock run at exactly the same speed as on the ground, because it had slowed down because of the speed, but sped up because of less gravity. And the answer to that is, for any slowly rotating planet anywhere, 1.5 times the radius of the planet. So if you put a satellite up, and Andrei, there's a calculation for you. I leave that for you as homework for the student. At 1.5 times the planet's radius, if it's slowly rotating, the clock will run at the same speed.
Thank you. Good. I'll take this. There's a related question from a member of public with name Timur, who asked, what happens with time when we get closer to a black hole?
Thank you, Timur. And I'm glad that you're there in England where you're asking that question right now. Timur, as you get closer to a black hole, you're going deeper and deeper into the gravitational field, and the time slows down more and more and more until when you reach what is called the event horizon, which is the Schwarzschild radius of the black hole that I talked about in a previous Astro-Chat. At that distance, from our point of view, watching you go into the black hole, time stops. And Kip Thorne, who recently got the Nobel Prize for his work on black holes, he had what he called the membrane paradigm for black holes, where from an outsider's point of view, watching things fall into a black hole, it all just gets plastered on the surface, going slower and slower and slower as the clocks slow down finally to stop at the event horizon. But from your point of view, your clock's running normally. If you fall into a black hole, you just go in. And we don't know what happens to you except that you make the mass of the black hole a bit bigger.
Thank you, Don. There is quite another fundamental question from Simon Fry, who asked, could you comment on how entropy causes the error of time?
Simon, no, I can't. If I may beg that question, that goes back to where I started at the beginning, like what really is time? And I can't answer your question. But Andrei's a physicist, and he's head of physics at Lincoln. So let's let Andrei answer a question. Andrei, over to you.
Oh, yeah, so now I'm in a light sport. Yeah, there's a concept what time is. It's really, as Don said, is a difficult concept, and indeed there is one of most enigmatic features in physics, this entropy, which what created, interestingly enough, when created in science when Industrial Revolution happened, and it was to basically help us to understand how thermal engines are running. Later, people understood it's actually kind of can be needed to be explained, not just engines and industry, but also how matter works, how atoms and molecules, how they kind of come together, melt, and so forth. The laws of this come in that the entropy is changing, and Don can say us about this thermal death of universe.
I would like to jump in at this point and just say to everybody, when I asked you that question at the beginning, what really is time? Do you know the next time you're at a party full of astronomers and physicists? Doesn't that happen to you? I mean, it happens to Andrei and me. Next time you're in a room full of astronomers and physicists, you ask them that question. And, you just did that to some extent, ask that to Andrei and me, and watch us start waving our hands and using lots of big words that don't sound like we really know what we're talking about. But let's look at another question.
Yes.
That one works to illustrate the problem.
There is a question about, again, time dilation from Matthew Arnold. Do time dilation effect have to be taken into account then measuring time periods of other planets from Earth compared to on the planets themselves?
Oh, the answer is yes, technically you would. And if you were interested, for example, in the details of the physics on the surface of a neutron star rotating nearly 1,000 times per second, you would have to take into account both special relativistic time dilation and general relativistic time dilation. And that's another kind of problem I used to give to my undergraduate astronomy students. Now, I'm wondering, don't any of you wonder about more questions on the measurement of time? There's lots of other interesting things that happened historically. You all like the physics. I need to remember that for future talks. All the questions are coming in about the physics and not about the history.
Yeah, and just let me take one question. It's a kind of philosophical, but also fundamental. Like light, is there speed of time, and can time be considered a wave or a particle?
That's a good, what is time? I wouldn't think of time as a wave or a particle, but in the standard model of the universe, at the earliest times, it's thought that time is quantized. There's something called the Planck time. It's about 10 to the minus 35 of a second. And so then time becomes quantized. I'm not sure that helps me think about it better.
Yeah. As you mentioned about the measurements of time, now it's kind of taken almost for granted that we exactly know what time is. Okay, exactly, it's maybe exaggeration, but we kind of know. But when we kind of started really to more or less kind of able to measure time in relative precision to our days, it wasn't really so long ago, was it?
No, it was in the last century. And since you mentioned that, this addition of leap seconds is just not only controversial, but it's litigious. There is a desire by people who run satellites, GPS systems, and other industrial applications that we stop having leap seconds. Because if you throw a second into the calendar, into your clocks, everything on the GPS global positioning system has got to be reset to take that into account. Many industrial processes care about time to that level, and this costs a lot of money. And so industry worldwide would like the world to agree to stop having leap seconds. The main people who argue against that are astronomers, because then the telescopes and the astronomical time begin to drift with respect to the time on the clocks. And my guess is in the long run, astronomers are not going to win this one. And what will happen is that we are going to have to take care of all the problems that arise out of that, rather than industry having to take care of all the problems that arise out of the leap seconds. The last attempt to make that change was maybe 4 years ago, and the vote went in favor of keeping the leap seconds, but I don't think that'll be true indefinitely. And then with time, the Earth's rotation will drift out of sync with the clocks. And thousands of years down the line, people are going to have to fix things. They're going to have to be a big fix instead of leap seconds. There's going to have to be a leap month or a leap something.
Oh, okay. It's a bit in the future for us. But there is a question about measurement and history in the same time by Andy Ellison. Did Galileo really use his pulse to measure the swing of a large pendulum?
Did he? I don't know the answer to that. Of course, I think of the pendulum experiment as being Foucault, who first set it up in the Paris Observatory and then later moved it to the Pantheon in Paris. Did Newton do that? Not Newton, sorry, did Galileo do that? I don't know the answer to that, Andy. Let's turn that one over to Andrei.
I actually don't know, but in any case, if I think practically, it probably will depend if he is very nervous while measuring or very calm. So results would be difficult to verify, I would say.
I mean, obviously there were pendulum clocks then used for time, but I guess it was Foucault who used the pendulum to show the Earth's rotation. And so I don't think I've answered your question, and let me leave it at I don't know.
Right. There is a kind of return question from John Walsich, who just kind of asking if 60 seconds per hour is something also from Babylonians.
Oh, yes, and I thank you for asking that, John. Let me now go into that. What the Babylonians did was they divided the circle into 360 degrees. That was because the sun's motion in the sky is very close to 1 degree per day. They knew the year was 365 days, but they had what was called a hexadecimal system. They actually counted in groups of 60. And those groups of 60 were divided into the 12s that I told you about earlier. So the Babylonians used a grouping of 60s, and 6 60s very nicely made 360. And that's why we have 360 degrees in a circle. You might have wondered about that. Why that number? Why not 100 degrees? Why not something nice and round? Well, because the people who made that up wanted it to match approximately the motion of the sun in the sky each day. And that's why we have 360 degrees. They then divided the degree, they subdivided the degree into 60 minutes of arc. And then they subdivided the minute of arc into 60 seconds of arc. Those were all angular measures. And it was only with the accurate clocks come the 15th century, when clocks could keep precise time, that we started dividing time into seconds and minutes. And we followed the pattern of the division of the minutes of arc and seconds of arc. And so that's where that 60-second division came from too. The Babylonians like that number 60, which is 5/12.
Thank you. Now we will add a little bit of time to our time, about 5 minutes extra, because we lost them somewhere in the middle. So I think to play with time is appropriate for the work for the talk about time. And I see there is answer about Galileo from a historian of science with nick name Minerva Bird, who says yes, Galileo did use his pulse, and Galileo's father was a musician. So that is answered. And then there is a question from Matthew Arnold. What have other cultures that did not use the Babylonian standard for the day choose to use? And do any still use their standards?
In terms of the days of the week, I think we're going to have to, because what I gave you with the Babylonians, oh, you mean in terms, does anybody have other than 24 hours? Worldwide, we're all on 24 hours now. I would think that most rural cultures throughout history didn't have hours. And I can tell you where I live in Africa now, if you're in rural Africa, the hour doesn't mean very much. If you go out on the road to catch the bus and the timetable says it comes at 4 p.m., you better arrive a bit early and just sit and wait, and you should bring food and you should bring a blanket because it might not even be today. And so that hour probably wasn't in most cultures, and it has spread around the world to be 24 hours. In terms of days, different cultures had different numbers of days in the week. And typically for most cultures, it was between 5 and 10. The ancient Romans had an 8-day week. In Mali, in North Africa, the Dogon people still have a 5-day cycle they work on, a 5-day week. And of course, the week originally had 2 functions. It was so that people, and almost everybody was rural, so that people could gather at a regular interval for 2 main purposes, one of them being religious, which is also social, and the other one for market, in order to trade. And so humans have needed to have a small group of days to gather regularly for social, religious purposes and for marketing purposes. But different societies have chosen different numbers, and that 7-day week is now spread around the world, coming out of that Middle Eastern culture.
Thank you, Don. I think we still have, of course, some questions and comments, but we would like also to give time to Don to have his dinner in South Africa, and his time is shifted.
May I interrupt you? I'm not having dinner now. It's 10 p.m.
All right, so
I've done that already before we met.
Right. Let me then just look here. There are several comments about Galileo, so obviously, and then John Leventhal writes that a legend goes that Galileo conceived his work on pendulum because he watched a long lamp swinging during a church service. He timed the swing of a pendulum with his pulse. So that is a bit of history.
It is. It also tells us about the quality of the sermon that day.
That is probably true, yes. Okay, so I think we now already extended our time till past. Thank you, Dawn, for this fascinating talk on time, and everyone who came to this Astro-Chat, and we hope to meet again in some future time and chat about.
We can meet again in May. I'm traveling in April, but if you'd like to do it again in May, then we can have a new Astro-Chat in about 2 months.
Yes, was some interruption with connection, but Don just said that we'll have like a leap time, and we will meet again in about 2 months. Okay, thank you very much, and apologies for interruption during our connection. Internet isn't perfect, but we managed, and I think we all enjoyed. Thank you everyone who came, who asked questions. Thank you very much, Dawn, and also thank you, Sergey, who is behind the scenery, managed to connect us all together. That we enjoyed this evening. Thank you.
Okay, thanks everybody for coming.
Bye.
Bye-bye.